Class is Professor Gavor. We're talking about part 2 of chapter 4, discrete random variables. And we'd like to cover, in this case, the geometric distribution, the hypergeometric distribution, which I'm assigned some problems, but I'm not putting it on the exam, and the Poisson distribution. So we'll start with the geometric. They're all these discrete distributions that we've talked about, starting with the binomial distribution, which is a series of Bernoulli trials in which there is basically, it's the same as saying there's replacement. Each individual one is independent. So this is still based on Bernoulli trials, where we pick something and we have, or we do something, we run the experiment, and we have a certain probability of success and a certain probability, 1 minus that probability of failure. So it's not only success, it could be the item of interest that we're in. There are one or more Bernoulli trials with all failures except the last one. So we keep getting failure, failure, failure. We're looking to get the first success. So you keep repeating it until you find success. You know, if at first you do not succeed, keep trying until you get it. That's what we're saying. So in theory, the number of trials could go on forever. Like if you're flipping a coin, the first time you get a head, you could theoretically flip all tails. It would be really astonishing that would happen. There would be a low probability that you would have an infinite number of tails or 1,000 tails. If you were to flip a coin and your success would be, first head would be in the 1,000th and first. So the probability P of a success and the probability Q of a failure is the same as in any Bernoulli trial, and is the same as it was in the binomial distribution, which was a series of Bernoulli trials. So I get P plus Q must be equal to 1. So the probability of the thing I'm not interested in is 1 minus P. X equals the number of independent trials until the first success. So if we look at this, the PDF here, if a random variable X, there's no formula in this for in Excel, because it's a relatively simple formula. If a random variable X follows a geometric distribution, then the probability of experiencing X minus 1 failures before experiencing the first success can be found as follows. So a probability of X, where I get my first success on X1. So I get failure, 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 X minus 1 times, and then I get success. X equals the number of trials till the first success. P is the probability of success on each trial. So if we look at an example, you're playing a game that you can either win or lose. There are no other possibilities until you lose. Your probability of losing is 57%. What is the probability that it takes 5 games until you lose? Let X be the number of games. So this is example 4.17 from the textbook. X equals the number of games you play until you lose, including the losing game. And X takes on the values 1, 2, 3. So in this case, when we talk about probability of success, it's a probability of losing. So P is our probability of losing. So let's look at how this works. Let's go to Excel. And I can make this, of course, bigger. And this is example 4.17, and it's geometric. And so we have, what do we have? We have the probability of losing, the probability of the item we're interested in. It's not really a probability of success. It's the probability that we're actually looking for is 0.57. There is no other parameter in this distribution. If you go here, there's no other parameter. The distribution is just X is GP. It's only the probability, because it could go on infinite. There's no N in this. So the probability is losing. So what's the probability of, so here we go. Let's do our X. And let's do our probability, our PDF, basically. So let's put X here. Escape X, delete PDF CDF, because rather than just try to answer one question, I'm encouraging you in every case to answer all the questions. Let me move this up here. I was good at this. These lectures wouldn't take so long. I'm going to make this is orange because this is a parameter and it's something we're going to keep fixed. I'll put a little box around that. That's the only parameter in this distribution is this 0.57. And if we change it, then we can change what happens. So what's our X? So I have, this is a probability that big X is equal to little x. And this one is going to be the same kind of thing. Copy, paste. Except instead of equal sign, we're going to have less than, because the cumulative is always less than or equal to the little x. And we're going to underline that. There we go. So there can't be 0 because I have to do one trial to see if I get success or not. So I get, and every one is going to be plus 1. So I can calculate this. Let's take it all the way down to 21 and see what happens. And let me right justify these. Let me make them bold. And so now what is this? My formula is this. It equals 1 minus p to the what power? Raised to the, in this case, it's going to be this x minus 1. Okay. And then I'm going to multiply it also. And then my success comes on the next one. So I'm going to make it, I'm going to put it on this side so I don't confuse. It's not multiplied in the exponent. Well, I think I can put it on this side. Let's try this. Times p. And what do I get? 0.57. Well, that's what I should get on the first try, right? What's the probability of losing in the first game? 0.57. So that worked out perfectly well. But now I want to do my trick of putting the dollar sign here because when I drag this down, I don't want the C1 to change at all. So what's the probability of losing on the second game? So it's going to decrease pretty quickly, and it goes to 0 very fast. So if I take this and I make them all 3 decimal places, you see it goes to 0 very quick. How do I calculate my CDF? I use the old trick of saying equals this on the first one, and then it's equal to the previous plus the current, kind of, for each successive ones. And if I take this down, you see it all goes to 1. Now, if I was to draw the PDF, which is what I do in almost all these cases, I would say insert, and I would take, which graph do I want? I would take this kind. I would take a bar chart, and what do I do to the bar chart? Well, I probably want to, I don't know if I want to put the values. I might not do that. That's hard to read when I have so many of them, and it will get all cluttered, so I'm going to go back to this, and what kind of, I'm going to click on the bars, and maybe I'm drawing too many. Since it goes to 0, maybe I'll only take it to when it gets to 0. Let me just draw 10 of them or 11 of them. Now if I say insert, and I go to the recommended chart and I pick that, that's much better. If I pick something with the numbers on it and I click on the bars, and what do I say? It would go over here, and I think I'm going to go over here and say 0 gap width. So that moves my graph like that. And then I'm going to put, what, white bars. That's what I usually pick, white or red. I pick white. I don't want any transparency, and let's make them 1 point. And so I do that. And it didn't actually do anything. So let's go back here. Borders. I got to click on the bars or it doesn't do anything. It has it. Transparency. I want 0 transparency. And yeah, that should work. I don't know why it's not making my borders white. I want solid line, it's making it blue. I want it white. There we go. And I have it now. So if I want to answer a question about this, what if it takes me to the third game to lose? That's where I get my first loss. It's 3%. But what if it's 3 or less games? It's 92. What if I want to play 6 games and, until I get my first loss? What if I get my first loss in a 6? It's only a 0.8% chance, and there's a 99% chance that you will have lost on 6 games within the first 6 games, 6 games or less. So I can ask these questions. What's the probability that I lose after 3 games? Well, what's the probability I lose after 3 games? I would be 1 minus the probability of it being less than 3 games. So it would be 8%. So you can answer all kinds of questions this way. If I change this, what if I change this to 50-50? Well, it brings the probabilities down. And what if I make the probability of losing only 25%? So I can expand these out. So this answer was 57. I'm going to leave it there. This is the way I like to set it up so that I can do what ifs with the probabilities, and I make sure I have enough trials so that as I change the probability, it works. So we looked at this. Here's the relationship. There's only one parameter, P. It's a probability of the item of interest, which we're calling a success. Now assume that the probability of a defective computer component is 0.02. Very small. Components are randomly selected. Find the probability that the first defect is caused by the 7th component tested. How many components would you expect to test until one is found to be detected? Well, that would be the mean. And if it's 0.02, what is the mean for this? The mean is 1 over P. Here's the variance, which is 1 over P times 1 over P minus 1. And the standard deviation is the square root of that, which is 1 minus P over P squared, which I think if you simplified this, it would be the same. It would be 1 minus P over P squared. But 1 minus P is the probability. So where do you expect to get the first one? Here, if I want to calculate the mean, I would say, probably let's put it over here, mean equals, in this case, 1 divided by 0.57, and that didn't work out well because I didn't put an equal sign, equals 1 divided by 0.57, or I expect to have 1.75 trials until I get my first one. So almost 2. Between 1 and 2, almost 2. But if you look at it, that's where it's going to be. These distributions are definitely always skewed because you're looking for the first success. Standard deviation. We don't really need the variance. I can figure out the variance another way. It's equal to SQRT. And what did they say it was? 1 minus P over P squared. So what do I get? Square root of, I put another parentheses, 1 minus P divided by, and then it's going to be P squared. And I put another parentheses, and I should be all set. So my standard deviation is 1.15. Most important thing, of course, is the mean. And we'll put this in yellow since these were calculated numbers. an output number. Okay, and what happens if I change it to, like again, 0.5? What happens to the mean? It changes to 2. Well, guess what? 50-50. This is until I get the first head. So if I get 50% chance of getting on the first one, I have a 25% chance of getting on the second one, and it just goes down all the time as I'm multiplying 0.5, 0.5. It's really 0.5 times x. So this is 0.5 times to the first power, this 0.5 to the 2, this 0.5 to the 3. So it's really 5 squared, 25, 5 cubed, 125, and it goes down. So it's supposed to be 625, so it rounds off to 0.63. It's not too crazily scientific. I mean, it's not like it's a mystery. You can like almost kind of guess to see where the numbers are. But of course you have to do it. So here's one. Assume the probabilities of a defect of a computer component is 0.02. Components are randomly selected. Find the probability that the first defect is caused by the 7th component. Well, what would I do here? This is example 4.2. So why don't I go back here and create one, example 4.20. And again, it's geometric. And what do I want to do? I think I want to copy all this thing over. Because this 0.57 here, 0.57 is this problem. Okay, so that's because I put a bracket there, which doesn't belong. So why don't I just copy this whole sheet? Copy. And I'll paste it here. Why did it do that? Because I'm not paying attention at all. Let's go here. Copy. So clearly I'm going to be screwing around with this stuff here. So let me make it bigger so you can see it again. Now what changed here? What changed? Well, in this problem, the only thing that changed, the only parameter is this is now going to be 0.02. And what do you think this is going to do when I hit 0.02? Well, I probably have to draw another graph. So, first of all, because this graph is picking up on the other graph, the graph didn't change, but look what happened to my probabilities. 0.02, 0.02. Maybe I need to make these so it says the mean is going to happen after 50. So after 7, I expect to get 0.018 because the probability of failure is so small. It's only 0.02. It's 2%. So let's make these 3 decimal places, and let me pull this down to there goes to 50. So where's my 50th percentile? It's right about 35, actually. So I hope I did this right. Anyway, if I was to graph this now, and let me graph it out to 50, I don't think it's going to be very interesting, but that's okay. What will I do? I'll say insert, recommended chart, and I'll put a chart like this in. And I don't think there's any reason to make more of a histogram of it than that. That's what it's going to look like. So at first it's 0.02%, or it's 2%, and then it just keeps going down. So where am I going to get my first failure? Because my failure rates are very low. It's 2%. The mean tells me I expect to get it at about 50. Because it's 1 divided by 0.02. And 1 divided by 0.02 actually comes out to be 50. So I don't know if that's really a compelling answer or not. I think when you're using defects, you're probably more likely to want to use a binomial distribution. Okay, so there we have it. Now let's move on to another distribution. So here's the mean, here's the standard deviation and the variance. And all right, so this is another example. A lifetime risk, you try this one, of developing pancreatic cancer is about 1 in 78. Gee, that seems awfully high. Let X be the number of people you ask until one says he or she has pancreatic cancer. X is a discrete random variable with a geometric distribution of where the parameter is 1 over 78 or 0.128. Now, if I take the mean of that, 1 over 78, if I take the reciprocal of that, it's going to be 78, 1 in about 78 people. So you're going to get that. What is the probability when you ask 10 people for this, they say they have pancreatic cancer? Well, how do I answer that? I don't even have to, I'm not even going to do it, but I would change this to 0.178. And it changes it somewhat. And what did they say? What is the probability that I must ask 10 people before one says? 10 people before one says, so that means 11. So it's a 0.025. And what is the probability that I have to ask 20 people? Or it occurs on a 21st trial. But the question is, let's read the question again. What is the probability you ask 10 people before one says he or she has pancreatic cancer? So I've got to ask 10. On 11th, I get the answer that I want, which is yes, I have pancreatic cancer. So it's 2.51% or 0.0251. What is that probability if I bump it up to 20? It becomes 0.43%. Well, what's the probability at 11? So that would be 21, 0.029. And what if I say at 11 or less, I get my first answer? Well, I'm going to get 88% chance that happens. What if I take it up to 20, 21, where I get my first success? But I say, what's the probability of me getting a yes before I get to 21? So that's 98.37%. Okay, and I think I put 178. It's 128, sorry. It's combining too many answers, so let's change that again. And so at 11 now, instead of whatever it was, it's 3.25%. And at 21, my first failure, or first person says they have it, is 0.83%. I don't have to wait till 21. The cumulative probability is by 21st, there's 94% chance that someone's already said they've had it. So geometric distribution, number of trials until you get your first item of interest to respond. So now let's look at hypergeometric distribution. You take samples from two groups. Basically this is like red balls and blue balls in a box. It's like playing cards. But the key here versus the binomial distribution is it's without replacement from the combined group. So you want to choose a softball team from a combined group of 11 men and 13 women. The team consists of 10 players. Each pick is not independent since I'm not putting the person back in the pool to pick my player for the team. So each pick is not independent since sampling is without replacement. In a softball example, the probability of picking a woman first is 13 of 24. The probability of picking a man second is 11 of 23. You could do this like diagram, but you're doing it 9 times. So you don't want to draw a diagram. This is not a Bernoulli trial. So the outcomes of the hypergeometric experiment fit a hypergeometric probability distribution where X is the number of items from a group of interest. Well, what's this distribution look like? Well, if we randomly select n items without replacement from a larger set, capital N, m of the items of one type that are my items of interest are n minus and n minus m of the other items that I'm not as concerned with. The random variable x has a hypergeometric distribution, and the probability density function looks like this. The probability of getting x of the, like, let's say in this case, maybe it was the male softball players, there's m things taken x at a time, and then you have the number of women. You don't have to worry about what that was, or not males would be n minus m and n minus x combination divided by how do you pick n things from n. So a softball team, how many people are we picking? A softball team, we want to choose a softball team. A team consists of 10 players. So we want to pick 10 from 23, and we're picking them randomly, and we want to know how many men are on the team, basically. Or you could do the complement of that and find out how many women are on the team. So it's called a hypergeometric distribution. So let's do that example and see how that works. So this is softball team hypergeometric. Let's make it HG. So let me go to my little thing. I'll make another one, and we have softball team hypergeometric. So what do we have? What is my n? And let me make this bigger so we can see it. Oh, I can't make it bigger until I actually enter it. So what do I get? I get n equals, I don't remember, 11 men, 13 women. So there's a total of 24. The item of interest, which we're calling M, is actually 11. And it happens to be male, but that's just, I guess, luck on our part that we're using the same letter. And this are parameters, which we'll put in orange so we know it's a parameter. So now I got X, and geez, I'm tired of typing the same thing all the time. It's always going to be this, so let me copy it from here, because I am lazy like you. There we go. So how many people are we going to pick? How many? We're talking about number of males on a team. 1. And so if I write it equal to that plus 1, and we said there's going to be 10 people on a team, so I take it down to 10. Because then what's the other thing? I forgot the other parameter, which is what? We have a set of n items. We're picking m, and well, we want to find out there are m items at one time. We're picking it without replacement, and there's a second time, so we're always picking. N is 10 at this point. I'm getting confused. Sorry. This is not the best lecture I'm ever giving. We have 24 people. We want to choose 10. So we have this n. There's 11 males, so n equals the number that we're picking is 10. And the number of m happens to be 11 males. So there's 3 arguments, like 4 arguments to this thing. And let me make this that way. And let's stumble through this the way, I don't use the hypergeometric distribution too much, but I know that if I go here and I want to say hype geometric distribution. So it's a sample, number in the sample, population, number in the population, and cumulative. So let's see what this is. If I open this up, click on it, it gives me this. So let me escape that. And where did my thing go? Okay. S. required, the number of successes in the sample. So that's going to be this number of males. I could have 0 males on a team up to 10. Number in the sample, required the sample size of the sample. So the sample size of the sample here is going to be, that's going to be my 10. Oh, where did my little thing go? There it is, sorry. Population, number of successes in the population. Well, that's going to be, there's 11 in the entire population. The number of the population is 24. So the sample required, the number of successes in the sample is going to be X. And then I just work backwards. So if I say, oops, sorry. I probably want to keep this off to my side here in case I need to refer to it. It equals hype geom, and what's my sample S? So in this case, I think it's going to be the X, which is going to be 0 in the first case. Number in the sample. Well, I think we want I'm guessing M. And then what's my population? 24. And what's the number, total number in the population? Or that would be 10. Then 24. And then I want to make it 0 because it's that way. So the probability of getting 0 men on a team is that. The probability of getting 10 men on a team, it doesn't like that because what do I have to do? I have to put dollar signs around everything, all the C ones. Dollar sign, dollar sign, dollar sign. So this is why I'm not going to test you on the hypergeometric. I want you to do some problems. And let's take it to 3 decimal places. And does it all add up to 1? And it adds up to 1. Now, how do I do the cumulative distribution? For me, it's just, rather than do that all again, I would just make that equal, and then I would do my trick where I say this is equal to the one above it plus the one next to it. Okay, yes, it doesn't like that at all. What did I do wrong? It's equal to that plus this. And if I copy it all the way down, it comes to 1. So again, if I want to make this a insert recommended chart, and I do this, I will get this. And let's say I'm only interested really in the mean here. So let's say the mean is what? I don't know, I don't remember. N times M over large N. N. So what are we talking about? N and M. N is 10, M is 11 divided by 24. So equals M times N divided by 24. So it says my average is about 4.58, 4.6. Well, it is. You can look at it here. It's going to be between 4 and 5. And it's closer to 5. Because the probability at 6 drops off, so it's going to be skewed this way a little bit. So right in here. Boom, that's how we do that one. There's a couple other problems you can do it. I'll let you do the lake one. A lake consists of 600 fish, 80 of which have been tagged by scientists. A researcher randomly catches 15 fish from the lake. Find the probability mass function for X, the number of fish in a researcher's sample that was tagged. So he's collecting 15 fish. And you've got to look at what it is. So you got 60, 80, and 15. What number is that? Big N is obviously 600. 80 of which have been tagged. That's little, I guess, M in this case. And then 15 would be, or N would be 15 the sample size, and M would be 80. So I would do it. Here's another one. Let X be a random variable. Denote the number of aces in an all 5 card hand dealt from a standard 52 deck. Find a formula for the probability mass function. Let's do that one. Number of aces in a card deck. So this is aces, and this is hypergeometric. And what do I want to do? I want to do the same thing that we had here. I think I want to copy. It's only going to go to 5, so let's do that. Copy. I'll place it here. And let's make it bigger. Okay, so how many cards are in a deck? That's what big N is, 52. How many cards are we picking in our sample? 5. How many aces are there in a deck of 52? 4. So you can't get 5 aces. And I really can't get 4 aces is such a low thing. Look at it, it's a very small number. So the probability of having 0 aces in a deck in a hand of 5 cards is 66%. The probability of getting 1 ace is about 30%. The probability of having 2 aces is 4%, and then it goes to 0.2%, and then it goes to 0. So again, if I was to draw this, what would I do? I would say insert, and I would get this. And now, since it's a small number, I'm going to put the probabilities on it, and I'm going to do my thing of reducing the gap. And if I go to border, I'm going to reduce the transparency. I'm going to make it white. I'm going to make it a little bigger and say OK. So there we go. So mostly it's going to be 0 deck. So what do we say the mean was? If we put the mean here, it was NM divided by equals 4 times 5 divided by 52, which is 0.38. We expect to get between 0 and 1, closer to 0 aces in any hand. So that would be 38.5%. Okay. That's a hypergeometric distribution. We're not going to test you on it. I may ask you a general question at most. All right, the next one is Poisson. The Poisson, good, and I got someone cutting the lawn near my house, which is always fun. So you get lawnmower noise. There are 2 main characteristics of the Poisson experiment. The Poisson probability distribution gives the probability of a number of events occurring in a fixed interval of time or space. If these events happen with a known average rate and independently of the time since the last event. So it's mean time between, independent. It will tell you, how many are occurring. The Poisson distribution may be used to approximate the binomial if the probability of success is small, such as 0.01, and the number of trials is large, such as 1,000. N is the number of trials, P is the probability of success. So the random variable X equals the number of occurrences in an interval of interest. So this thing has a distribution of Poisson with only one parameter X. one parameter mu, which is the average. But most of the rest of the world uses the Greek letter lambda for the mu in this. The mean of the interval of interest. So the notation is Poisson. Another way of looking at it is Poisson lambda. And lambda is greater than or equal to 0. Greater than 0 has to be greater than 0. The distribution variables, or the x, goes, and they use k here, or at least the thing I copied this from, goes 1, 2, and it could go up to infinite. The PDF is lambda to the k times the exponential constant, the natural exponent constant, which is like pi, a non-repeating decimal, to the minus lambda divided by k factorial. The CDF is there. The mean is lambda. The variance is also lambda, surprisingly. But that's the magic of the natural exponent, which is 2.7 blah, blah, blah. You can look it up. Theoretically, you've taken college algebra already, so you, in some sense, remember that. Okay, so here's one. This is problem example 4.29. This person, Leah, has an answering machine. Receives 6 phone calls between 8 a.m. and 10 a.m. So what is the probability that Leah receives more than one phone call in the next 15 minutes? So the number of phone calls Leah receives in 15 minutes, well, is 15 minutes is a quarter of an hour. So that's going to be x. If Leah receives an average of 6 phone calls in 2 hours, and x goes from 0, 1, 2, 3, and she could get an infinite number of phone calls, even though that's not very probable. She receives an average of 6 phone calls in 2 hours. Well, there are 8 15-minute intervals in 2 hours, so let's look at it this way. She gets 1/8 times 6, or 0.75 calls in 15 minutes. So mu is 0.75. So they multiplied these two numbers together. The average that she got times 1/8. So now mu is 0.75 for this problem. So this distribution is, capital X is distributed Poisson with a mean of 0.75. So let's look at this. That's what we have. Poisson 0.75. So let's do example 4.29. And let's call this Poisson. Well, since I'm going to have the same kind of things, I'm going to copy this stuff over. And I probably edit all this, so let me just copy some of this over, the headers. And boom. So let's call this, let's make it bigger. I'm only going to have one parameter here. The hypergeometric has 3 parameters, so I don't need these. Let me delete 2 of these. And this is mu, or lambda, depending on how you want to look at it. And we said it was going to be 0.75. In a 15-minute period, she expects 3/4 of a phone call. And I'm not from Scandinavia, so my decimal place has to be a period. Now, so how many phone calls could she get? She could get 0, or she could get equals that plus 1, and I can copy this down. I don't think she's going to get a lot of phone calls, but I'll take it up to 20. And now I say it's equal to Poisson, and there's Poisson distribution. X, and the mean, and whether it's cumulative or not. So I'm going to say X is that. What is this? My mean is that, and I don't want it to be cumulative. I want the PDF, so it's always 0 or false. And 47% chance that she's going to get 0 calls. And let's make it 3 decimal places. And let me put the $sign between a C and a 2, because when I cycle this down, I want the X to cycle, but I want the mu or lambda to remain the same. There we go. So it goes to 0 very quickly. And if I want to do it the other way here, I could do it this way. I say equals Poisson for the cumulative distribution, and it's still going to be x, comma, mu or lambda, whatever you want to call it. I'm so used to calling it lambda. And now we're going to put 1 because I want it to be the cumulative distribution, but it's not going to change. But if I do this, it cycles to 1 very quickly. And let's make it to 3 decimal places. And there we have it. So what was the question? Well, we did how many of this do you expect? What's the probability? What do we say the mean was? Well, this is also, mu is equal to the mean. So she expects 0.75. It's also equal to the mean. That's the nice thing about this. And it's also equal to the so if I graph this, I want to graph it till about here because I don't have to graph all of that. I say insert, recommended chart type. We'll go there again. And if I want, I can if I click on this and there, I can reduce the gap width to 0. I can put a white border. I'm tired of white. I probably want to use red at this point, but there we go. And if I want to change it, which is too late now, it's going to go back to that. So I have to do the whole thing again. Did I mention I was tired of white? So I'm going to use red this time. Well, let's be crazy and use orange. There we go. And if I change the mean to 1, we get that. If I change the mean, if she gets, 2 calls in that time, it changes this way. So the bigger I make the mean, she gets 2.5 calls in that time period, it becomes less skewed. The smaller I make it, the more skewed it is. So what would we have? 0.75 for the first one. There we go. If I do this again, I'll probably just copy this and change it for whatever other example we do. Now, another way of looking at it is this NP. So if a customer receives 10 emails every half hour, what is the probability that the customer service center receives more than 4 emails in the next 6 minutes? Well, now I have to figure out my mu again. So this is they can give you a lot of these curveball kinds of problems. Another way of looking at me, what's the probability of getting a call? Is I get 10 emails. So 10 emails in a half hour, and I'm looking at how many per minute does that mean? 10. So I get 1/3 per minute because I have to divide 10 by 30 to take it from 10 emails per half hour to emails per minute. So it's going to be 1/3 of an email per minute. So what's the possibility I get 4 emails in the next 6 minutes? We could do that. So here's example 2. According to Baden, an email management company, an email user gets an average of 140 emails per day. Let X equals the number of emails an email user receives per day. The discrete random variable takes on the value 0, 1, 2, 3. The Poisson distribution is that. The mean is 147. What is the probability that someone receives exactly 160 or at most 160? Well, now it's a little bit different because if I put this down, I've got to have a lot. I've got to have a lot of rows, right? So what example is this? Example 430. Example 4. 30. So maybe rather than do the entire distribution, and it's Poisson, maybe I just want a general Poisson calculator. So I'll say mean, and in this case we know it's 147, and so that's what the mean is. We already know the standard deviation, I can calculate it right away, is going to be equal to SQRT, which stands for square root of that 147, and I get 12.12. And what these guys, they got 12.1244. So now maybe I just want a PDF and a CDF, and rather, since it's going to be so many, I got to have hundreds of things here. I have X, how many I expect to see, and we'll just make this calculator up. CDF. So this is be something I want to enter. So these are our parameters, we said. That's what we're given. Let's say we enter something here, which will be, I don't know, what do we want to make it? That's where we enter something, and maybe that's too dark. We'll make it very light green. And we're going to output two things. We're going to calculate two things. So let's make those in yellow. And so now any number I put in here, it'll give me the PDF and a CDF. So let's just put any old number in there. Let's put 100 just to start. And if it says, I want this to be Poisson distribution of, I'm looking for that many, I put too many parentheses, sorry, that many, comma, that, comma, and notice you can put, if I want to put false, I could, well, I won't do false. I could put the word false in there too, right? But false is also 1. And it comes out to be very small. If I make it a number, if I make it to 5 decimal places, it's not going to be very much. My CDF is going to be the same thing. So let me copy this over. I moved it, which is not what I want to do. I did it again. What's wrong with me? I didn't drag it. But now I want to change it. So it's not, instead of C7, I want to be B7. And instead of D3, I want it to be C3. And instead of false, I want it to be true because I'm doing the cumulative distribution. Yay, good for me. So there's my cumulative distribution. So what did we say the mean was? 147. So it's slightly above 50%. Because the skewness is not going to be, the probability is not going to be 50% for the mean. The probability is going to be 50% for the median. And where's the median going to be? The median is somewhat less than that. So let's say it's 140. It didn't like that. What were we at? 147? Oh, the probability is only 3% there. But the cumulative probability is 50%. So where's the cumulative probability at? 145. Ooh, it drops, it changes pretty quickly. So it's about 146, 147, somewhere in there. It's pretty close to 147. So what was the question they were asking? What's the probability of getting exactly 160 or less than 160. So let's put 160 in there. 160. I get 1803, 0180. I took it to 5 decimal places. And this one is 0.86663. So it's 8666. We get the same thing they get. And then there's one more. The probability of a low seismic activity. So on May 13th, 2013, starting at 4:30 in the morning, the probability of low seismic activity for the next 48 hours in Alaska was reported to be 1.02%. Use this information for the next 200 days to find the probability that there will be low seismic activity in 10 of the next 200 days. So I have a probability of next 48 hours is 1.02. So it's just a probability. Find this for the next 200 days. So I want to multiply that by 200 days. And P, they get 2.04. Now the question you can ask, I think the probability, it doesn't matter 48 hours but that's the number they're using, the daily, or just the probability of seismic activities in a period of time. Let's assume that probability doesn't change, and let's assume it's per day. So we multiply 200 times 1.02 and get 2.04. So now if I go to my calculator that we had here, and let me change that. I can copy my calculator over. I don't have to do this problem again. I can make a new one. This is example what? 4.32. Example 4.32. And it's also Poisson. And so I go up here. Let's say I just copy this thing. Copy. Place it over here. Life is good. I make it bigger. And now instead of 147, we had 2.02, right? 2.04. So it tells me my standard deviation is going to be 1.43. And I'm looking at the probability of 10 days have to calculate. Let's see, the probability, so low seismic activity, to find the probability that there will be low seismic activity in 10 of the next 200 days. So I put 10 there. It's 0.0004 or 99.9999%. I don't know what they got here. So probability of actually getting 10 is 0.000045, which what do we have? 0.1234. If we make it bigger, what do we get? 45. Same thing, and if we make this bigger. So sometimes the reason I need so many decimal places is these are low probability events. So I have to go up many decimal places to get an answer to this. So the number of decimal places, here's an example where the number of decimal places is dependent on hold on 1 second. Let me call you right back. The number of decimal places is in the context of the problem. So that's how you solve problems with Poisson, geometric and hypergeometric. I've given you homework assignments. You can see how I've done it. I'll put this file up in there and the PowerPoint in the Canvas for this week, and you should be all set to go. And I'm going to say thank you very much. I'll see you again soon.